I'm going to be talking about optimal approximants and orthogonal polynomials in several variables. This is joint work with Alan Sola from Stockholm University. So first, we should probably talk about what optimal approximants are. So if you saw Chris's talk on Monday, you'll recognize a lot of this. Here I'm saying, okay, take F in some reproducing kernel Hilbert space. We're going to have a couple of standing assumptions, but if you want to just be able to follow along well, just assume this is the Hardy space. So take F in your function space. Its reciprocal might not be in the function space. So in our nice example here, 1 minus z is definitely in the Hardy space of the disk, but 1 over 1 minus z is not. So we can do Taylor polynomials for example, 1 over 1 minus z, and those do give an approximation, but they might not give the best one. And that means we should also talk about what we mean when we say best, because, you know, there are a couple different ways. So when I say best approximant here, the optimal approximant, I want to find a degree n polynomial, Pn star, that minimizes this norm p times f minus 1. So you can think of this as approximating 1 over f in your function space, or you can think about it as finding the closest point to 1 in the subspace f times the degree n or less polynomials. Okay, optimal approximants, cool. But my talk is also about orthogonal polynomials, which means I should probably explain why these two go together. So there's a nice theorem from Arveson, Leah, Secco, and Sola, and I've written it in some generality here. Basically, it kind of makes sense. You're talking about an optimal approximant, a closest point. There should be some relationship to orthogonality here. And it turns out that if you have an orthonormal basis for a weighted space, where you just change the inner product, you can recreate the optimal approximant by using that orthonormal basis. And similarly, if you just take the difference of consecutive optimal approximants, you'll be able to get orthogonal polynomials, weighted by some constant that you can figure out. So now, though, let's flash back to the 1970s. So in the 1970s, there were a collection of electrical engineers who were interested in what they called planar least square inverses. So these are secretly just optimal approximants. The engineers were mainly looking at the Hardy space of the disk, that's the least squares part, and they actually also were interested in the bidisk, which is cool because I'm talking about multivariable optimal approximants. Now, one of the things they were looking at were reflections of orthogonal polynomials in weighted spaces, and they also looked at separable functions, and they saw, okay, well, these optimal approximants are clearly related to these orthogonal polynomials, and we can do some stuff in two variables, but it's more restrictive. There's actually also a mathematical paper from 2015 by Benito, Condori, Leah, Secco, and Sola, where they look at the two variable case as well. And they run into some of the same problems that the engineers run into. And we've finally resolved those. So that's exciting. The engineers were looking at this in terms of applications to filtering theory. And if you don't know what that is, it's fine. What you should notice is that what the engineers want, filters to be stable when these optimal approximants have no zeros in the bidisk. So this was their goal. They wanted to be able to find an optimal approximant of a certain degree, and they really wanted to be able to tell easily if it had zeros in the bidisk or not. Okay, so then we actually should talk about what happens in several variables and some of the difficulties that people have run into and our solution to that. So several variable case. The first thing we want to think about when we think about the several variable case is I'm talking about polynomial approximants. So I probably want to be able to talk about what degree my polynomials have. Before, remember I said the degree n polynomial. Well, in several variables, you have a couple different ways to think about degree. You can think about total degree, where total degree 1, this just means you add up all the exponents and it better be 1 or less. I have total degree 2 here as well. Add up all the exponents, it had better be 1 or less. One of the things the engineers look at is they look at multi-degree, and we looked at this a little bit too. You might want to be able to say, I want the approximant that has degree 5, 6, or whatever. So it would have the highest exponent in Z1 would be 5, and the highest exponent in Z2 would be 6. But remember, I'm saying, okay, I want the degree n polynomial. So, okay, multi-degree 1, 1. Sure, that will give me this polynomial, which will have it has an extra term beyond the total degree version. And multi-degree 2, 2, the engineers called this grade 2. This has like way more terms. And it turns out that neither of these is particularly helpful for us. Because remember, we want to be able to talk about these orthogonal polynomials. I would really like to be able to take the difference of two consecutive optimal approximants and recover an orthogonal polynomial in the weighted space. But for these, this doesn't work. For an example, let's have our function, the function that we are weighting our space by, be 2 minus z1 minus z2. Perfectly reasonable function. And we'll take another function that I've named g. We'll just have it be the function that's equal to z1 on the Hardy space of the bidisk. And if you look at the difference between my optimal approximants, P2 and P1, in both of these cases, I'm not going to be able to rebuild Z1 from this. The differences of my optimal approximants, like hopefully I get orthogonal polynomials still, but I might not get enough. I might not be able to span the space. So it turns out the way to solve this is to choose a monomial ordering. Now, the examples I'm showing today are going to be in 2 variables, but this monomial ordering that works for however many variables your little heart desires. You just set it. We chose to look at the total degree ordering, and I think we call it degree lexicographic because I'm saying Z1s come first and higher powers of Z1s come first, and then we go up by total degree. So when you set that, instead of talking about the polynomials of degree less than or equal to n, I'm going to say Pn, this is going to be the polynomials that's the span of the first n monomials under this ordering. Okay, so one thing, I'm just going to show you a diagram here real quick. We found it in the 2 variable case to be somewhat enlightening to lay out our monomials this way. So we've got our Z1s going up along that top line, our Z2s going down along that bottom line. And you can read degree lexicographic order here by reading down each column from left to right. This is actually pretty useful. I'll hopefully have time to show you why later, but for now, you just need to know that that's the monomial ordering we're using. So we take our monomial ordering and we take our subspaces Pn, and then from here we can define the nth order polynomial approximant to 1 over f. You just define this as the projection onto that subspace, f times Pn of 1. It's the closest point in that subspace to 1. This is basically exactly the same definition as we have in the 1 variable case. We just have to be a little more careful about degree. And as I say here, in other words, it's the unique polynomial that minimizes this norm just like we want it to. So it turns out that ordering the monomials this way is exactly what we needed to do to be able to translate the matrix method for computing optimal approximants. So this is just kind of a reinterpretation of some previous results. You can compute optimal approximants by building a Gramian and then solving a system of equations. And you can't do this unless you include every single monomial. And it works well if you have just like 1 variable, because then you just go up by degree. But now we actually need to look at each monomial and add them in 1 at a time. So we get this nice method. And using this, let's look at a couple of explicit computations. So the first explicit example I'm going to look at here is on the bidisk. Let's again just say the Hardy space of the bidisk, although we can talk in more generality too. I'm going to look at 1 minus 1/2 z1 plus z2. This is a generalization of that 1 minus z on the disk example that I talked about on the very first slide. And you can see, okay, I have computed some optimal approximants. They do seem to be going up 1 monomial at a time, so that's exciting. And it turns out that when you take the difference of these, you do actually get some orthogonal polynomials, which is awesome. So let's look at another example. Let's look at 1 minus z1, z2. So this is a different potential generalization of 1 minus z. But here we run into some problems. You'll notice that on this slide, I've got P0 I've got P4 and I've got P12, but I don't have anything in between those. And that's because P0, P1, P2, and P3 are all equal to 1/2. And P4 through P11 are all equal to 2/3 plus 1/3 Z1, Z2. And same thing with this P12. We only get a difference in our optimal approximants when we get to a new power of Z1, Z2. So this is distressing. If we take the difference of two consecutive optimal approximants, we sure aren't going to get something good, right? We're going to get 0. That's not necessarily going to be helpful. So we can't use the optimal approximants to recover the orthogonal polynomials. We won't get enough of them. We're not going to get all of them. And in some cases, for some functions, we're not going to be able to get any that way. You'll recognize this definition. It looks very similar to what Chris was talking about. We can define a function, say it's weakly inner, if inner product of g and a monomial times g is 0, as long as that monomial isn't a constant term. So again, we're having a weakly inner function defined this way. Now, if it's weakly inner, it turns out that all of its optimal approximants are just going to be equal to that first term. So Pn is going to be P0 for all of them. And nicely, if a function is inner, then it's weakly H2 inner. Cool. But one of the things that's different in the multivariable case that you don't see in the single variable case, in the single variable case for the Hardy space, inner and this weakly inner are equivalent. They are the same thing. But in the multivariable case, they don't have to be. You can have functions that are weakly inner, but not classically inner. So some engineers, Delsarte, Janin, and Comp, I think, yes, they found a power series example, but we're actually able to talk about a slightly more explicit example. If you look at the Shapiro-Shields functions, these can be constructed using determinants. And I'm just giving one example here, but you can show it in general, that the Shapiro-Shields function associated to points, this will give a function that is weakly inner, but not classically inner. So again, here I'm showing the 1-point Shapiro-Shields function for the Hardy space of bidisk, but we also look at this in the paper for the Bergman space of the bidisk, and you can talk about it more generally. Okay, so these give examples of weakly inner functions in any reproducing kernel Hilbert space, like I said. Okay, so I still have plenty of time. So then let's kind of shift gears again and think more about these orthogonal polynomials in weighted spaces. So remember the example I was talking about? I was saying, okay, sometimes the optimal approximants aren't enough to recover all of the orthogonal polynomials. And let's look at this particular example and really dive into it. We're going to look at 1 minus Z1, Z2. On the slide, you'll see I have 1 minus A times Z1, Z2. This is because we're actually able to show some of these results in more generality. But for the purposes of this talk, we live in the Hardy space of the bidisk, and we're looking at 1 minus Z1, Z2. So here are our optimal approximants. Remember, they stay the same between 0 and 4 and between 4 and 12, and then until you get up to Z1, Z2 cubed. So if we try to do differences here, we're not going to get enough of our orthogonal polynomials. But we can do Gram-Schmidt. Gram-Schmidt still exists. We can do Gram-Schmidt on the monomials with our weighted inner product. Because remember, these orthogonal polynomials, they're orthogonal in the weighted space. So here's our weighted inner product. Here's the results we get if we do some Gram-Schmidt on some monomials. And one thing you'll notice is that things look kind of predictable. 1, Z1, Z2, sure, orthogonal. And then here at phi 4, the first term where I would have Z1, Z2, now I have something more exciting, right? You compare phi 4 to phi 7 and phi 8. Hey, look, those look pretty similar, right? If you continue doing this, you'll get up to, say, phi 12. Remember, that was the first term that has our z1 squared, z2 squared in it. And if you continue this, phi 17 and phi 18, those look pretty similar to this phi 7 and phi 8 here. So, all right, let's look at phi 4, phi 7, and phi 8. Remember I said these look kind of the same. If you look at phi 4, that's the first term that has z1, z2 in it. Phi 7, that's the first orthogonal polynomial that'll have z1 squared, z2 in it. So now I get to show you why I think this diagram is useful. So here's our diagram. I have lined up my monomials so that you can read degree lexicographic order by reading down each column and left to right. And here I've circled the monomials that appear in each of these orthogonal polynomials. So phi 4 is in red, phi 7 is in teal, and phi 8 is in lime green. Look, they clearly line up here. They are on these, what we've been calling the diagonal. The red one, phi 4, that's on the main diagonal. Phi 7, well, if you look at the terms in here, you'll actually see that it's basically the same as phi 4, but we've just multiplied by z1. That's what we see in our diagram here. It goes up to there. Same thing with phi 8, it goes down there. Nice. Now we can also talk about phi 12, phi 17, and phi 18. These are my other examples. So here they are. Phi 12 is on our main diagonal here. Phi 17, just multiply everything by z1. Phi 18, multiply everything by z2. Awesome. So we actually have a formula for this. And again, we've got it in more generality, but I think this is a nice version for this talk because these are familiar polynomials. And what this is telling us is that in its heart of hearts, this is a one variable sort of problem because it all works on the diagonals. It's just you scrooch up or down a diagonal as necessary, but it's all built from the stuff on the main diagonal. And the main diagonal is just kind of recreating that one variable question. So if we take this, we can see, okay, here's some polynomials. They're very nice. They're the orthogonal polynomials for 1 minus z. And then it turns out that you can form an orthogonal basis for 1 minus z1, z2 just by, again, scrooching up or down as necessary. And you'll just be able to recreate it that way, which I think is pretty cool. So now let's actually still have time. Let's look at another example. And now instead of thinking about the Hardy space, we're going to think about the Drury-Arveson space on the ball. You can do this again in more generality. We can look at a scale of Drury-Arveson spaces. But for now, we're just going to look at the Drury-Arveson space. It's nice. And here we have to change the constant. We'll have 1 minus root 2 over 2 z1 plus z2. This is just to make sure that we still have that 0 on the ball. So again, you run the same matrix computation to compute some of your optimal approximants. And you still have some nice symmetry because it's still a symmetric function that you're starting with. And now, if you were to run some Gram-Schmidt on your monomials, these are the orthogonal polynomials you get. And I don't know about y'all, but I think those are pretty dang pretty. Look at them. They're so symmetric. And it turns out that, let's look at our phi 1. This is the first term that has a z1 in it. It just got a 1 and a z1. The z2 is just got a z2 and a 1. Phi 4 here, well, it forms that little box. And if you were looking for the orthogonal polynomial that first has z1 squared, z2 cubed in it, inside this little box here, those are exactly the monomials that are going to appear, which is pretty nifty. So now we actually were able to find a closed form for the orthogonal polynomials in this weighted space. And the key is the fact that it does stay in that nice little box. So we've got this nice formula with our coefficients, our phi hats, and it has a ton of factorials in it. So this works really nicely in the Drury-Arveson space. Unfortunately, though, you don't get that same sort of cancellation in the Hardy space of the ball. So, or the Hardy space of the bidisk. So, oh, no, you do get it in the Hardy space of the ball, but not of the bidisk. So the ball is special. I think we kind of knew that. But I still think it's pretty cool that we were able to get the closed form for this. And again, we have it in more generality as well. All right, so I think it's been 20 minutes, so I'll stop there. My summary here, things are harder in several variables. You've got to choose the monomial ordering. There's some question about which one might be best to choose. Weakly inner doesn't imply inner here, or weakly inner implies inner. I think I had that back. No, I had it right the first time. Weakly inner doesn't imply inner. You can have the Shapiro-Shields functions. And then we've got some other neat stuff that we've done. We found a closed form for orthogonal polynomials for 1 minus z1, z2. And we found a closed form for 1 minus something times z1 plus z2, which I think is pretty neat. So I'll stop there.
Thanks, Meredith.